We cannot hear Zheng. I can saw you speaking.
怎么了？中断了？怎么了？那他就可以说话。那我什么时候打开呢？
Yeah. So, excellent.
All right.
Huh. All right. So, Yujie, it's your turn now.
Okay. Okay, Professor Zheng. I think it's my first time to do, so thanks for joining the EML webinar. I think we had several questions for you.
Okay.
Maybe the audience can share success and experience. So the first one, it's I personally know that you had been working on solid mechanics. And was very successful in the field. So from the talk you will be given, it's very different. So can you tell us what motivated you to switch gears 20 years ago and started another successful journey on environmental mechanics, or explore the dynamics of sand and dust storms? It's very different from conventional solid mechanics talk, right?
Yes.
Yes. Can you tell us a little bit about?
Okay. Yes, as you mentioned, I did switch my research field. In my early career, I was engaged in several topics in the field of solid mechanics, one of which is about nonlinear deformation of thin plate governed by the von Karman plate equations. They are two nonlinear differential equations with two variables coupled each other. As we know, when the plate is a circular one and subjected to a concentrated node at its center, the von Karman equations have singularity besides nonlinearity and coupling. And many scholars, both in mechanics and in applied mathematics, had been devoted to seek the exact solution. But what they got only the analytic approximate solutions, in which the famous one was given by Wei Chang Qian, in Chinese, Qian Wei Chang.
Okay.
I proposed the exact solution and proved its convergence. And also I invested the convergence of the approximate analytic solution, such as perturbated solution and iterative solutions. I found these approximate analytic solutions include Qian's solutions are not always convergent. Beyond the center, beyond a certain range of the node, these solutions may be wrong. This work was finished in 1987. Then, in the early 1990s, I was attracted by the electromagnetic solid mechanics. At that time, one of the key problems is how to characterize the magnetic force of the ferromagnetic material structures in a magnetic field. Many scholars use to calculate the magnetic force directly by the Maxwell's stress tensor or Faraday's law in electromagnetism. But our research found it is wrong, since the boundary effect of magneticized materials deformation should be considered. And then we gave a new formula of the magnetic force. My another work is about giant magnetostrictive materials. I presented a linear constructive model, which is an analytical one, and the model's parameters are all materials constants that can be measured in practice. So some scholars evaluated this constitutive model is convenient for practical application. Of course, I have also studied the scale effect of Young's modulus and found the external electric fields has an effect on the Young's modulus of nanomaterials. As for the switch to explosion the wind-blown sand movement that was in the later 1990s. As you know, I have been working in Lanzhou University, which is located in the northwestern China, where sandstorm frequently happened. Both the fifth and the sixth largest desert in China are about 300 kilometers away from Lanzhou. These deserts have been expanded quickly, and the two deserts tend to merge. Desertification caused the local citizens and the farmers to lose their land, resulting in frequent sandstorm, which in turn aggravate the desert expansion and air pollution. In several cases, the sandstorm even caused the train to overturn. Another phenomenon is lightning in sandstorm, which means there exists a strong electric field and which can cause communication interruption. Therefore, sandstorm and desertification are considered as a major environment disasters in northwestern China. I noticed from news and reports that sandstorm also burying people in Africa, Australia, and the United States, and even Japan. In my opinion, wind-blown sand movements is a typical mechanics issue, so I switched to it, and what I concern is how to improve current forecast accuracy of sandstorms, how to realize the prediction of the expanding speed of desertification, and how to effectively prevent its expansion. That's all. I hope my words can answer your question.
Yes, that's a very detailed explanation about how you.
I have a question.
Yes.
Sorry, Yujie.
Yes, go ahead, please.
Yeah, so I have a popular book you wrote about a sandstorm.
Oh, yes.
Yeah.
With my PhD students, Ping Wang. Yeah.
Okay, yeah. This popular book, so today, because a sandstorm is something a lot of people are interested in, but very few people actually studied anything about a sandstorm in this EML community. Are you going to, in your talk, are you going to describe sandstorm, just a phenomena itself?
Oh, actually, in this talk, I will focus on the expansion of desert, and also focus on the electrification. Yeah, I think the maybe the audience of the EML webinar, maybe most of them in solid mechanics. Right. So what I will talk is about the common issue, that is the multi-scale issue or trans-scale issue that maybe a little better for the more audience to understand.
Yeah. Also, you mentioned the early part, your work dealt with effect of a magnetic field on deformation. Yeah. So
yes.
I haven't studied your work in that. I never heard you talk about these things myself. I only heard you talk about a sandstorm. That's why I know.
Yeah.
So, so I don't know. Yeah, I just want to relate to see if it's similar. We also work on much later in 2000. We started to study the effect of electric field on deformation, especially on soft material, because in soft material, electric field can cause extremely large deformation. Now, in terms of mathematics, are they similar? Have you looked at these things?
Actually, no. What we focus on the electromagnetic solid mechanics only for the mechanism materials and structures. And sometimes, and in my opinion, maybe a little bit complex for the magnetic solid mechanics, since we have to solve the field of magnetism on the magnetized materials, the magnetic fields in the materials and out the materials. So the boundary or deformation maybe has a strong effect to the result.
Yeah. What materials typically show strong coupling between mechanics and magnetic field? What kind of
I see usually some steel materials can be magnetized in a strong magnetic field, but in the small the intensity of the magnetic fields may be up to 2 or 3 Tesla or anymore.
Okay. Hey, Yujie, back to you.
So, all right. So you mentioned that you changed the field 20 years ago, but so for most of the people like me, I feel like the sandstorms was investigated by physicists who cares about the atmosphere and devoted on sand dunes, sandstorms, and desertifications, because that's more environmental related. So what's your perspective when you choose this field, so that you feel mechanicians can add new understanding to this field and contribute our insights or research.
Okay. I would like to answer it from maybe two aspects. Firstly, wind blows and movements include sand flows or sandstorms are a kind of complex complex dynamic process of granular materials in wind field. No matter the collisions of sand particles on the surface and their saltation and suspension in air, or the turbulence of wind field and the particle-laden flow, they are all typical research objects of mechanics. So we define the wind blows and the movement as a typical process featured by the multi-phase medium like gas and the sand particles, the multi-phase coupling like wind field, thermal convection, electrical fields caused by the wind blown sand, gravitation fields, and so on. And also the multi-scale in time and in the space, such as particles and centimeter scaled for sand ripples and kilometer scaled dew films and sandstorms. Secondly, as you said, geologists and atmospheric physicists have contributed their efforts to the wind blown sand movements. However, the methods they adopted were based on the early theories in the fluid mechanics. For example, they used the Planck's boundary layers theory to simplify the wind velocity to a logarithmic profile, but ignore the effect of turbulence. Or they use the large AD simulation method to consider the turbulence, but ignoring the impact of moving particles near the ground surface on the turbulence. In atmospheric science, it has been widely accepted the concept of gusty wind. In Chinese means 阵风，一阵阵的那个风 ，gusty wind, to describe the wind field. But our research found the gusty wind is inaccurate from the perspective of wind energy. That is, most of energy of very large scale coherent structures in the wind field are lost by gusty wind. So new theories and methods achieved in mechanics should be introduced to make better understanding and better prediction on wind blown sand movement. And in the same time, the research on wind blown sand movement may give us a chance to develop new theories and methods for characterize the multi-phase, multi-field coupling, and the multi-scale and the strong nonlinearity problem, which is a common scientific problem in natural science and in engineering. So our research is from the perspective of mechanics have provided solutions to some problems that they have not been able to solve, such as transcale simulation of dune fields and predict the desert's expansion speeds. And also our researchers have overthrown some existing understanding. For example, electric fields in Sandstorm were previously considered to be uniformly oriented upward, but our finding finds the electric fields varies upward and downward alternatively with the height. On the other hand, mechanical research also have the responsibility of introducing the modern theories and understanding of the fluid mechanics into the physics of windblow sand and atmospheric science and even earth science, so that they could make prediction and forecast more accurate. And it also embodies the role of mechanics in promoting scientific progress, advancing the continuous improvement of the quantitative level of the related disciplines in engineering and other natural science. So, in my opinion, the role of mechanics is indispensable. That's all.
Can I ask a question here?
Can
I ask a follow-up question? I have Professor Zheng. This is Tang Li from University of Maryland. So as you explained this sandstorm problem, right? This is such a different problem from what we have been working on as a typical solid mechanics community. Right? We look into materials, different properties, soft, hard, plastic deformation, elastic deformation. Now for the problem like a sandstorm, as you mentioned, that you could have very different length scales, right? For example, the sand dune or when the sandstorm are forming, they are in the scale of kilometers or even larger, right? Tens of kilometers. But the sandstorm itself is essentially because the tiny sand grains, they're so small and lightweighted, so the wind can really blow them up, right? So then for the sandstorm, we're talking about the sub-millimeter length scale, right? So I can imagine in this problem, you have several length scales over there probably is governing the whole process. And also you mentioned there could be electrical field forming inside the sandstorm. That's something I never heard of. So that also means that it's multi-physics. So when you first look into this problem, if you look into more from the larger scale, and for example, you can introduce for example, the fluid mechanics understanding into how to understand the sandstorm formation, how they propagate. Now, my question is it necessary to look into at the different length scale, especially is it a better approach to go top down from larger scale to the tiny small scale of each individual sand grains, or a bottom up? My natural feeling is probably it should go from large scale to smaller scale. Then the question will be, does the mechanical property or other property of the individual sand grains matter in this sandstorm formation?
Okay.
Just curious about this.
So I'm trying to answer your question. In my opinion, for the sandstorms maybe is very complex, And what I think in mechanics, we can focus on some key, the key parameters, such as how many sand particles inches from the surface of the Earth. And in the atmosphere science, they usually assumed and treat very simply. And in the mechanics, we can make maybe more accurately analysis to give the boundary condition or the initial condition of the atmospheric science the models better, and hence their accuracy of forecast. And also you mentioned the up-down or down-up, and that is I will mention in my this talk. We measured electric fields in sandstorms, and then inverse solve the equations to get the charge of charge to mass of particles. So we use the large scale measurement result to get the small the charge to mass ratio. This is the very small scales. So sometimes the both situation I will talk for maybe from the particles movement to the large scale, such as the sand dune fields, and also I will talk about how to measure the mesoscopic parameters, such as the electric fields in sandstorm, and to get the small quantities such as charge to mass ratio, which is difficult to make accurately measured. So your questions, I just can give my answer in this two aspect.
Hey, Jimmy, you want to say a few words? Jimmy.
Oh, Xiaojing, this is Jimmy Xia from Nanyang Technological University in Singapore.
Yes.
One of the co-editors in chief of EML. Thank you very much for giving this webinar. And Zheng initiated this. Teng Li from University of Maryland actually made this an art.
Yes.
So a lot of people are very interested. We also have another editor, Sulin Zhang from Penn State over here. So yeah. So thank you very much for giving this seminar. We're looking forward to hearing it.
Okay, thank you.
Okay, time is Xiaojing, can we ask you to share your screen?
Okay, okay.
And then Yujie, you will formally introduce Xiaojing when screen is up.
Okay. So Professor Zheng, when you share the screen, I will introduce briefly you to the audience from the world around. I think a good morning for people from North America, and good afternoon for people in European, and good evening for people in Asia regions and so on. So today I'm very glad, and it's an honor for me, also a privilege to introduce and also host a distinguished speaker, Professor Xiaojing Zheng from China and from Lanzhou University. We know that extreme mechanics lattice, the webinar is basically trying to promote the extreme boundary of applied science. And tonight we are going to hear one of them, which is relating to the scope of extreme mechanics webinars. It's relating to environmental and climate. The speaker, Professor Xiaojing Zheng, is an academician of Chinese Academy of Sciences and also a member of the World Assembly of Sciences. She is now a director of the Center for Particle-laden Turbulence in Lanzhou University. And she is the editor-in-chief of the Acta Mechanica Sinica, which many audience may have published the papers here. If not, welcome to publish papers there. Her research interests include a high Reynolds number or turbulence, particle turbulence, interaction in multi-phase flows, multi-scale modeling, and simulations of environmental disasters, such as dust storms, dune fields, wind blows, sand flows. And tonight we are going to hear her talk and research on multi-scale and trans-scale analysis in particle-laden turbulence. Let's welcome Professor Xiaojing Zheng. Please, Professor Zheng.
Okay. Yes. Hello, everyone. I'm Xiaojing Zheng, the speaker of today's webinar. Now I'm in Lanzhou University, Northwestern in China. Firstly, I would like to express my sincere gratitude to Professor Zhigang Shuo for inviting me to give a talk on EML Webinar. And also thanks Professor Ten Li for giving helps to this talk. Mr. Yujie Wei is a professor in the Institute of Mechanics of CIS in Beijing. Thanks Yujie for agreeing to act as a discussion leader of this talk. Thank you all for watching and participating. As we know, extreme mechanics later has quickly become an influential high-level journal in the field of mechanics. It is a miracle which is created on the one hand by the editor's ingenuity and personality charm, especially EML Webinar initiated by Zhigang, which demonstrates Zhigang's persistence in academic pursuit and personality cohesion in the community. On the other hand, it benefits from the forward-looking and leading position of this scope and aims of the EML. In my opinion, these topics represent the frontier and the chance of today's mechanics. And most of these mostly sounds focused on the solid mechanics. But what I will talk here is Sandstorm like this. Sandstorm obviously is a kind of fluid, but it is one kind of very extreme phenomenon in nature, and it should be an extreme mechanics issue. Besides the sandstorms, besides that, sandstorm is also called particle-laden turbulence or two-phase flow. The flow phase is turbulence and the particles movement are random. So Professor Barchan and Professor Eaton, they are very famous, at least in fluid mechanics. And also the center of the turbulence research is in Stanford, also very famous research center. And both published a paper in this famous journal and pointed out the turbulence and the multi-phase flow are two of most challenging topics. When combined, they pose a formidable challenges and makes and the inherent stochastic nature and the random distribution make both experimental measurement and the numerical simulation far more difficult. And also in this 125 scientific research, the number 43rd is about this. The key words is the general theory, the turbulent flows, and the granular materials, and both are related to sand movements. So, in my opinion, the wind blow sand movements is the one of the typical case mentioned by this question. And also, I think a deep understanding and accurate description of wind blow sand movements may be helpful to establish or test the general theory. Besides the linearity and the randomness, the multi-scale is also a very important feature in particle-laden turbulence. From the particle movements, from particle movements to the sand flow, to the sandstorm, all are related to the particles movement, and their scales, both in times and in spatial, are different, are very different. So the micro and the mesoscopic process rented this one, but underlying laws and the mechanisms are very different. So different laws and the mechanics work on different scale, which is that the feature of multi-scale issues. So what we talk today only focus on the multi-scale and the trans-scale analysis on particle-laden turbulence, since trans-scale analysis is not only in fluid mechanics, but also in the solid mechanics. I will give two examples. One is formation and evolution of dune fields, and another is sand grain charge and electric fields, and to show how we analyze them in quantity. And I would like to start with the background and the motivation of my group's research in Lanzhou University, and finally give a summary. And this is the photo of sandstorm happened in Qinghai, northwest of China. It fronts the edge just like a sand wall. And this kind of sandstorms frequently in the northwestern and the northern region of China, the times up to 30 days per year. And in these regions, the desertification is also serious, since here there are several big deserts. And in the desert area, sand dunes have various shapes. These strips, as shown in this picture, are sand dunes named transverse dunes or linear dunes. And this kind of dunes commonly found on the edge of desert named Barchan dunes. And these dunes are immigrated in sandstorm and forced the local citizens to leave their house. This situation happened not only in China, but also in a lot of countries, such as in Argentina. You can find the age of the desert was expanding, and the Barchan dunes was inviting into farmland and into the city. So how to predict the expanding speed of desert age, and how to predict the migration speed of sand dunes accurately, and is an urgent and significant issue. For this issue, it is necessary to realize the quantitative simulation on the formation and evolution of desert. However, as we mentioned, from sand particles motion to the formation and the evolution of desert, or also called the dune fields, is a transcale issue, both in time and space. So we need to realize the transcale simulation from this macro one to this macro one. And the second example is the lightning. I'm not sure you can see this. The lightning phenomena in sandstorms, which indicates a strong electric fields in sandstorm. Such lightning phenomena is also observed in volcanic eruption. It means the moving particles are charged. And these phenomena exist widely in the industry and the outer space. And the studies have reported that the electrostatic force of the charged sand particles in windblows and electric fields play an equal role to gravity. And in this figure, this is the for the wind speed, and this is for the sand transport rate. And you can find this curve for the uncharged, and this is a positive one, the negative one, and this is the positive one. So you can find the deflection is opposite, and also different polarities act opposite effects, and also the electric force enhance the lifting of the particles, and the blue dots shows the charged result, and much higher than this line. Okay. Also, researchers found the electrostatic force of particles will inhibit agglomeration of the particles, and these structures disappear when the particles are charged. And also, the charged particles in Sandstorm attenuate the propagation of electromagnetic waves, and also we can find. So you can find the gamma, that means the mass ratio, charge to mass ratio, and the electric fields are two key physical quantities. And for the electric fields, it is a macro quantity, and it is easy to measure by instrument. But for the gamma, it is a micro parameter, since the diameter of one sand particle is only several micrometers. It is not easy to measure. And then at present, there are two types of methods for directly measuring the particle charge to mass ratio. The first is the trajectory deflection method, and the second is the Faraday cylinder method. And both are difficult to accurately measure the gamma. And for this one, sometimes you cannot guarantee the only one particles into this facility in natural sand flow. And for this one, the neutralization of the collect positive and negative charged particles make the gamma smaller. So in these research papers, the gamma usually assumed as the constant. And on the electric fields, as we know, in the fine day, there exists an electric field in atmosphere called a fair weather electric field. It originates from the negative charge on the ground and the net positive charge to the atmosphere. So its direction is downwards. We denoted the values the positive one. However, in sandy weather, these measurement results show the electric. The fair weather electric fields. For these fields, its intensity is about 120 foot per meter. And from this measurement result in sandy weather, you can find the electric fields is up to 15 or the 200,000 Fu per meter. Also, this field measurements founds the values is -1, which means the direction is pointing upward, opposed with the fair weather electrical fields. By the way, we should notice that the existing measurements are single point measurement and near the 2 meters height. Okay. Besides that, the instrument they used, such as this one, is too large, so that it has strong interference to the wind field as well as surround electric fields. And based on these existing measurements,
Hey,
Yes.
Xiaojing, we lost you.
There's a disruption of the internet.
Oh, okay. Whoa. All right.
What can we do now?
What can we do now?
Yeah.
Right.
Let me check.
Yeah.
Ask her to join again, I think.
Yeah. Yujie?
Yes, I'm contacting.
Yeah.
Yes.
It's okay. Okay, Jimmy, you can say something about EML.
Sure. Yeah. This is EML webinar series, and we do it every Wednesday, early morning in US time, US Eastern time, late evening in China time or Beijing time, in my case, Singapore time. And this is the brainchild of Zheng's, and he proposed this, and it's been very popular. And so first of all, I'd like to thank all of you, all of the participants for joining us today and for your support. And we have a process of selecting the speakers, and we're trying to balance the speakers in different fields, but also we would like sometimes to have maybe a few speakers in one particular area, either in sequence, or sometimes we have a few speakers who decided to invite some of the collaborators to present as a group. That's also a very successful model. And for each of these webinars, we have a discussion leader. And the discussion leader sometimes would also invite prominent people in that particular field to provide comments. So
Yes.
these are all very, Xiaojing is back, I see.
Yes.
Sorry, we lost you, Xiaojing.
All right, great.
I'm explaining to the audience what the EML webinar is. But since you're back, why don't you continue your presentation?
Yeah, we'll need to set you up again.
Yes.
We cannot share our screen.
You need to allow her to use the skin again.
Yeah. So
Make her
she has a multiple. We don't know which one.
Oh, we have two. Yes.
Make both of them. Both of them.
Both of them.
Yeah, both of them.
It's working now?
No. No.
No. Yeah. Keep trying because Professor.
Okay. Okay.
All right. Keep trying.
All right. Good. There must be some sandstorm somewhere. Just detect.
Yes.
Is it working now? Okay.
It's okay.
It's working. Yes.
Yeah.
Okay.
Oh, that's
okay. So continue.
Yes.
Thank you.
Yeah. So the instrument. Okay, this instrument may have a strong influence to the wind field as well as the surrounding electric fields. And also based on these existing measurements, some researchers made a speculation that under the action of gravity, the large particles with positive charges move near the ground of surface, while the small particles with negative charges suspend at higher altitude. So this speculation is relative over the positive. So our question is, this speculation hold in real sandstorm? And another question, as we mentioned, then how to get the gamma, since this is a very small one, and we want to get. We want to using the observation data to get these small quantities. So it is also a transcale issue from large scale to the small one. Okay, let's talk about the first example, simulating the formation and the evolution of the dune fields. This simulation is from the small one to the large one, so we call it the upscaling simulation. And can we directly get the dune fields by calculating each particle's movement, just like ab initio calculation? If so, it would take a huge amount of calculation. Then, if today's supercomputer could provide a huge amount of calculation, whether the actual calculation is okay, our answer is no, because the dynamic process on different scale are dominated by different mechanism and the laws. It is because it is the multi-scale issues. And let's see this slide. And this is the sand ripples. They are virtually similar to the dune fields, but the sand ripples have a saturation length scale much smaller than this one, according to our simulation. It means the growth of sand ripples cannot evolve into the sand dunes because different particles and mechanisms, such as particle and bed collisions, and for this, the siltation and deposition and erosion are included. Okay, our approaches goes as follows. First, the first step is dividing the simulation region into sand body element. The region is generally flat, sandy surface with slight but random distributed fluctuation. And this area maybe is about 100 square kilometers, for example, and the area of sand body element is pre-given. For example, 1 meters multiple 1 meter. But the thickness of the sand body element is determined by calculating the sand flux. And the second step is dividing the evolution time and calculating the sand flux one by one. The evolution time may be 50 years and is divided into a lot of time interval delta t, which can be pre-given, for example, 1 hour. And the sand flux on each sand body element in each delta t is calculated by these equations, and for the particles motions and for the wind fields respectively. And actually, from the particles movement to sand flows, it is the first transcale from transcales in which the splash functions and the PDF of liftoff velocities should be determined. And having calculated the sand flow flux, we can get the sand flux, siltation duration, and siltation distance on each sand body element in 1 delta t. And the third step is calculating the thickness of the sand body element. And from sand flows to the sand body element, this is the second transcale in which the erosion process should be analyzed and to get the erosion probability and the covering factor. And these two new statistic quantities to derived by the surface, by analysis, the surface erosion of the sand body element. And this is the derivation process of these two statistics, and quite complicated. I will skip it due to the time limit. And then finally, we get the thickness of the sand body elements. And the fourth step is calculating the transportation distance of these sand body elements. And actually, this is the third transcale in which we need to determine the fifth statistic quantity we called transportation factors, and also the derivation process is a little bit complex, and we also skip it. And having got these transportation factors, and then based on the principle of conservation of mass center, we can get the transportation distance. And repeating above process for all sand elements, and in each time step until the preset total time is completed. And using this simulation scheme, we realize the simulation from the particles movement to the sand dune fields. The whole process consists of 3 key upscaling leap, which is similar to the trip jump. So we called this transcale scheme as the trip jump model. It should be mentioned again, and every upscaling leap depends on the statistical analysis on the dynamics of sand groups, including the collisions, the splashing process, the surface erosion, and deposition. Okay, let's see our simulation result. And this is our simulation result for the transverse dune fields, much similar to the real one. And this is our simulation result for the Barchan dune fields, and also very similar each other. And these figures show the dune's migration speed. The black lines are our prediction result, which very close to this colored dots, which is the observation result. So our simulation have a good agreement in quantity. And also, this is result for the dune height. And also the black line is our simulation result, and the color dots are the observation results. And we can find the dune heights and the increase with the sandband thickness. And also for multiple prevailing wind directions, this is the 2 prevailing wind directions per year, and this is 3, and this is the 4, and the simulation result very similar with the real one. And also we show the expanding speed changes with the vegetation coverage and the wind speed respectively. And you can find the expanding speed decrease with the vegetation coverage, but increase with the wind velocity. And this results are very helpful for combating desertification. For example, this region is at the edge of desert in northwest China. These square lattices are made by the wheat straw hull to prevent sand particles taking off. And the lattice paved in whole region, just like this. And our question is, it is this one, it is the only one or only pattern, and using our simulation on the dune fields, we found the effect of this pattern, just like the stripped covering is the same to the whole covering, but reduce the cost nearly 70%. In other words, using our new covering pattern for this area, maybe about 30 kilometers square, can reduce by 20 kilometers square and save 25 million yuan in cost. Okay, now let's talk about the second example, how to get the sand grain charges. As we mentioned, this is from the large scale to this the small one. So we call it as downscaling inversion. At first, let's see how to calculate the electric fields in wind-blown sand flows. According to the formula of electric field raising a point charge, its electric fields in an arbitrary point of the space can be calculated by these formulas. And here, ρ is the space charge density per unit volume, which is related to the charge to mass ratio gamma and the dust concentration m. So calculating the n, which can be get just as we mentioned for the sand dune fields, and then assume the gamma as this one, we can get the electric fields by this formula. So this is the forward problems. But if we denoted these formulas as G no gamma, and from this one to get the electric fields, and the inverse calculate is to get the distribution of gamma, and by measuring the values of electric fields, and this actually is inversion problem. That means from E observative values to get the gamma, the smaller the one. And okay, let's see how to get the measuring values of electric fields firstly. And our measurements were carried out by the Qingtu Lake Observation Array. We call it QLOA. Qingtu Lake is located in the northwestern China and is a dry lake. So its bed is flat. We built the observation array there. This is the main tower, 30 meters in height, and with this small tower, 5 meters in height, and totally the 32 small towers. And ultrasonic anemometers and the dust concentrations instruments are installed on the main tower to measure the wind velocity and the dust concentration synchronously. And with this array, we got the 7,400 hours data, including wind velocity, dust concentration, temperature, humidity, electric fields, in which 595 hours data are high quality stationary data. And the observation result obtained by this array have published on the JFM, the Journal of Fluid Mechanics, and the station was praised as the notable. And based on this array, we deployed 11 measuring points, in which 4 points in the space-wise direction, and 4 in the vertical direction, and 3 in the streamwise direction. And finally, we can find that these 3 points, major points, are very important for the accuracy of our inversion result on the electric field. And on the other hand, the electric field instruments is made by ourselves. Its size are much smaller than this traditional one. So the effects of probe size on the measurement accuracy is observably reduced. And this is our measured result, the data. In April of 2017, we catched 3 strong sandstorms. Here shows the result. This for the electric fields, this for the PM10 particles concentrations, and for the visibilities, and for the wind speed, and the red line for the direction, and the temperature for this one, and the humidity, like this. And from this figure, you can find the direction of the electric field in a sandstorm are not only in the vertical, but also in the streamwise and the span-wise. And also the vertical electric fields shown by these red lines, you can find is selective. So which means the vertical electric fields is its direction is in upward. And this is for the first sandstorm. And this is for the second one. And you can find the electric fields intensity is up to 118 K per meters. And for this case, the PM10 concentration is very high, and the visibility is very low. And also, this is for the storm 3 measurement data. The 3 storms from these 3 sandstorms will last 24 hours in total. So we get a lot of data. And also you can find in these 3 storms, the vertical electrical fields showed by the red lines always the negative one. So our question is it always true at any height? I means our results are same with the existing experiment measurement. So is it always true at any height? The others for the height is about 2 meters, and for ours is 5 meters. And also another question is, how about the spatial distribution of charges and polarities? And for this, to solve these questions, we need to solve these inversion problems. Okay, this work just published on the Nature Communicators. And this is our inversion process and inversion region. The grid point N is about 9.6 meaning to ensure the accuracy of the inverse electric field. Then the equations can be rewritten, and we're using the Gaussian method to discretize these integral equations. So the equations can be rewritten in the matrix form, in which these are measured electric field data. Totally M is equal to 19. And this is calculated by this one. And for this is unknown. Is unknown, but the N is about 9.6 meaning. In this case, the equations and N much greater than M. So the equations is ill-posed in mathematics. And the solution, that means the solutions may be not unique and stable. So for this question, we have to transfer the original issue posed problem into the well-posed minimized key-Horner functional problem with regular method and minimize the GCV functional to serve an optimal lambda. And then when the optimal regularized parameter lambda is chosen, and having regularized the solution, and we can get the rho, and then according to the concentration, dust concentration, we can get the charge to mass ratio gamma. Okay, let's see our validity of the inversion method. We analyze the relative error analysis about the relative error changes with the number of measuring points, and you can find the relative errors decrease rapidly to the 10%, and also we can find if we have no stream-wise tars, the error will up to 40%. So the stream-wise tars play a very important role. And this is the analysis about the residuals, and also can find the result are stable with the time. And also we close the validation. You can find the measurement result given by the black lines with very close to the inverse reconstructed electrical fields. Okay, having verified our inversion accuracy and stability, let's see the result. And this is the distribution reconstructed space charge density. And the blue means the negative one, and red is positive one. And you can find the blue, no matter in the stream-wise, and the span-wise, and the vertical direction, the blue color and the red color are alternated like mosaic pattern. And this figure clearly shows the reconstructed space charge density at the center point along the height and at a different moment. It means that polarity changes, alternating, and which means is not always negative over positive along the height. And the mechanism may be related to the turbulence, in which the low velocity region and the high velocity region are alternated. And the small particles in turbulence gather in the lower velocity region, and the large one are relatively uniform distributed due to their inertia. And this is the structure for the electrical fields, and for the in the part of inverse region. And enlarge this one, we can find in vertical direction the distribution of reconstructive the electrical fields is very different with the existing result, in which the dark line means the upward pointing, and the green lines for the downward pointings. So you can find the upward and the downward and the upward again and the downward also like the mosaic patterns. Okay, and this is the reconstructive vertical electrical fields in Sandstorm varying along with the height. And you can find the upward and the downward flip alternative. So we can conclude the existing speculation is not correct. And this is the space change density varying with the PM10 concentrates. And you can find significance linear relations, and its lobe is gamma, and varying with the height too. Okay, this is our the result. And finally, we give the summary. The first is we realize the simulation of the formation and the evolution of actual sand dune fields. And the second is electrical fields and the polarity of sand charges in sandstorms are not negative over positive. And the third, in my opinion, is two typical cases of multi-scale issue, and one is upscaling and another is downscaling. For the upscaling, maybe the statistical analysis is very important, but for the downscaling, sometimes we should pay more attention for the inversion problem, since the equation may be ill-posed. Okay, I know the time is over, but take this opportunity. I would like to say some remarks about the EML. And inspired by Professor Zheng, I have been advocating and promoting the development of extreme mechanics in China since May last year. And this is in the Institute of Mechanics and invited by Yujie. And I gave the brief definition on the extreme mechanics, that is the study about extreme properties and the response of materials under extreme conditions. And also the fields and the topics of extreme mechanics include the 5 direction topics. And finally, in my opinion, the development of extreme mechanics research system is currently facing challenges. The first is new theories, and then new methods, and new technologies, and new mechanisms. And finally, I think the Newton's mechanics was born in the 17th century. And for the continuum mechanics, it was established in the 19th century. How about the 21st century? And how should the mechanics develop? And how mechanics continue to promote the other disciplines in natural science and engineering? My answer is extreme mechanics, and we're expanding the boundary of mechanics. That's all. Thank you for your attention, and finally graduated my students and the young colleagues and NSZC project support. Thanks.
Thank you,
Okay.
Professor Zheng.
Thank you. Thank you.
Yeah, can we ask you to unshare your screen so we can see all the panelists?
Thank you for the inspiring talk, Professor Zheng, and also for promoting extreme mechanics. That's exactly the journal and the webinar aim for. Okay, it's time for questions for distinguished guest and the audience. If you have questions, please raise your hand or send the message via the chatting board so that we can.
Yujie, can I have a question?
Yes, please.
Okay, this is Jimmy Xia here. Thank you very much, Xiaojing. Very interesting talk. Completely different scale, which is we, myself at least, are not very familiar with. Let me follow up with Teng's question. The question he asked before you start your webinar or before you start your lecture. His question was, there's this top-down approach versus bottom-up approach. So the top-down approach and bottom-up approach are the starting point of very different scales. So let me pose a scenario. Let's say that I'm an experimentalist. I do experiment. I have a wind tunnel. I can have a very small wind tunnel of very small size. And I put 1 cent grain in there. I blow wind and watch how the cent grain moves. Certainly this is not, this cannot represent the real case. All right, I expand my wind tunnel to a larger size. I put 100 grains of sand in there. I blow it. I watch how the grains of sand move. Still, that cannot represent the real case. I can have another wind tunnel which is 50 or 10 meters long, or another wind tunnel which is 100 meters long. I put a lot of sand in there. So from a very small wind tunnel to a large wind tunnel, at certain point, my experimental result is representative of the real case. What is this transition range? Is it a kilometer? Is it 100 meter, 10 meter, or something? That's maybe that's the bottom-up approach that Teng was referring
to. So you want Professor Teng Li give the answer?
No, I'm asking you the question. This is related to Teng's question.
Yeah, I don't do the experiment you mentioned. So I'm not sure what result you got. I think maybe the results are very different for the only one particles in very small wind tunnel with a lot of sand particles in a little bit large wind in large wind tunnel. Since I have not got the experimental data, I just imagine the results are very different. The reason may be maybe there is another mechanism such as the collision between the particles. So the mechanism may be different for a lot of particles with the one particles. Actually, at least this one is reason.
So there must be an emergent behavior somewhere.
Yes, yes. And also in fluid mechanics, there is another parameters. We call it the zero number. And the different scales of wind tunnel, maybe the zero number is different. So the zero number is very important, which may give obviously influence to the particles motion and also the flow in the wind tunnel. So now at least the two reasons to make the results different.
Since I'm cued by Jimmy, can I chip in a little bit here? Ask a related question. So when Jimmy said that, okay, when you try to do the experiment in the wind tunnel, right? So you scale down the size of the whole phenomenon from the real sandstorm to a wind tunnel being 1 meter, 10 meter. Now, in this case, shall we also scale down the particle as well? Instead of using the sand, maybe we should consider the dust. This is actually the similar question I meant to ask. So what's the difference between sandstorm and dust storm? For example, in the northern part of Shanxi, right, you have a lot of dust. So what not covered by plants, right? So the dust particles are much smaller and lighter weighted than the sand grains. Are there major differences between the sandstorm and dust storm? I hope that's a similar or related question to Jimmy's.
So you want me to give the answer, or
yeah. So yeah, that's a question for you because you're the expert here. So, for example, what's the major difference between a sandstorm and a dust storm? Because the particles are a very different size and
yes.
as well.
Yes, I understand what you mean. In my opinion, in the dust storm and the particles diameters is very small. I means maybe PM10 or smaller than PM10. But in the sandstorms, the diameters of particles are various in large range, and also in the respective of the fluid mechanics, there is another parameters we called Stokes number. For Stokes number, for the dust particle and the sand particle, the Stokes number is very different. They have different interaction with the flow. I mean, the large particles maybe with the large Stokes number, and in the sandstorms, this kind of large Stokes number may influence the interaction of the flow, and this kind of interaction different with the particles, the diameters, and also depends on the Stokes number. So maybe in the fluid mechanics, this is different. But if just we want to in common view, the dust storm, the concentration maybe is higher than the I mean the sandstorms conservations maybe is higher than the dust storms one.
So it's like you only need a small volume to represent a continuum medium if for dust storm, but
Yes.
for sandstorm you need a larger volume to make it a continuum like. Does that make sense?
Yes. Yes, for the maybe in the dust storms, the particles just follow the wind speed, and but for the sandstorms, the particles motion movement, maybe including the suspension and the saltation and the collisions of the between the particles.
Okay.
Let me answer more in mathematical terms. So in mechanics, in mechanics, of course, we have dimensional analysis, right? But the physical idea you need to put into dimensional analysis is some fundamental length scale and time scale. So in a sandstorm, what is fundamental length scale? It's a sand particle size or something else? For example, just to provide the context. So in regular hydrodynamics, of course, we all know hydrodynamics is supposed to describe the motion of molecules, but molecular size doesn't come in, does not come in.
Yes.
Right. So, but in sandstorm, would sand particle size come in as a part of model?
In my opinion, maybe it's depend on the different the issues. Yeah. For the sandstorms, maybe the small scale is is related on the particle size, but for the materials in solid mechanics, maybe small scales is the smaller one, and we cannot vision it by us. So it depends on what's the issue we studied.
Yeah. So let's move on. Yes.
Could I ask a question? Sorry, my camera doesn't work, so I just can ask a question.
It's okay, please.
So I know the professor, dear Professor Zheng, thank you for your interesting talk. I noticed that you simulated the dune field by using runs. from your governing equations to calculate the Venetian flow. My question is, in your experience, how much is the difference between the simulation and the actual situations, and whether it is necessary to consider the influence of turbulence on sand dune simulation? Do you think the impact of turbulence on sand dunes is important? And what are the impacts?
Okay. Your question is
the effect of turbulence on the simulation of dunes.
Yes, it's a challenge for us. As you mentioned, we really simulated wind fields by rents, which means the turbulence actually not considered. So in order to consider the influence of the turbulence, I ask my younger colleagues to do some simulation for considering the turbulence. So could I ask my young colleagues, Dr. Hong Yu, show some his recent result?
Yeah, sure.
Yes.
Okay. So how about Hong Yu, Dr. Hong Yu? He is my PhD student, but now he works in the Lanzhou University, and recently he got a new result. And Hong Yu is online.
Let's check.
Hong Yu, can you just press the hand-shaped button, and we'll promote you to a panelist.
I see him in the attendee list.
Just promote him.
Okay.
All right.
And make him a co-host.
Yes. Actually, his result is very interesting, and the result shows the influence of turbulence is obvious.
Hong Yu?
Hong Yu Liu, right?
Yes. Yeah.
Okay.
Thank you. Do you hear me?
Yes.
Do you hear me?
Yes, we do.
Okay.
In process of simulating the depth field, it seems that the RANS is used to calculate the winds and flow. My question is turbulence important to the formation of the depth field? If so, what are the effects?
Okay. So Hong Yu, you can show your recent results. Okay.
Okay. Thanks for your question, and thank you very much, Professor Zheng, for giving me the opportunity to answer the question. It's my pleasure.
Yes. Try to share your screen.
Okay.
Share your screen.
So Yujie, while he figures out how to find sharing screen, you invite somebody else to ask a question?
Yes. Hi, Xiao, please.
Oh, yeah. Very interesting talk. I think it's a very important problem. I'm Xiaojing from University of Texas, San Antonio. I have one question. You show, using the straw pattern, square pattern to prevent sand motion. So my question is, that's a flat pattern on the surface. Sometimes I heard we can also plant bushes, trees, to prevent the sand move. So my question is, the tree bushes, they're vertical, they're 3D. So which one is more effective, the bushes or the straw patterns?
Oh,
from mechanics point of view, maybe.
Yeah. Actually, as we know, maybe the bushes is a little bit better than the straw lighted patterns, since the bushes a little bit higher than the straw.
While your student can do a simulation, say which one is more effective.
Yes, yes. No, we have not a simulation for the bushes, but we can try. We can try.
I think Hongyu is ready.
Okay.
Yes. Hongyu, please.
Oh, thank you, Professor Wang and Professor Ma, for this question. It is very important. Recently, we just did some analysis on the influence of turbulence in the simulation of a sand dune field. Results suggest that the turbulence have a significant impact on evolution of sand dunes. As mentioned by Professor Zheng, our simulation programs of a sand dune field can be regarded as a triple jump model because the model includes 3 transcale processes from the sand particle movement to sand flow, then to sand body element, and finally to the
Hongyu, we only see the slides from Professor Jin. Maybe your slide on the influence of turbulence is not shown, or is it?
Sorry.
So your slides on influence of turbulence is not shown, I guess. What we see is triple jump.
Hongyu, just directly show your result, the simulation result. Don't show the slide of my slide. Show your result.
Yes.
Okay.
Okay. Therefore, I will explain the effectors of turbulence from 3 aspects. To introduce the effectors of turbulence, the improved deflecting velocity predictive model of neural turbulence provided by Professor Marsick is introduced into the simulation program of the wind blowing sand flow. These two figures shows the statistical average of sand flux and citation distance. The red symbols are results by turbulence and the black symbols are results by rains. We can see that the turbulence increases the sand flux and the average citation distance of the sand particle in the wind blowing sand flow. The sand flux increase reaches 11%, and the citation distance increase reaches 13%. Moreover, the greater the wind velocity, the more significant the influence of turbulence. As a bridge of a transcale, the sand body element is also affected by a turbulence that cannot be ignored. These two figures shows the variation of the erosion thickness and transportation distance of a sand body element with the friction velocity, where the dense lines represent results by turbulence and the solid lines are results by rains. We found that the turbulence would increase the thickness and the transportation distance of a sand body element. The greater the wind velocity and the smaller the particle size, the more significant the effect of turbulence. This may be caused by the increase of sand flux in the turbulent sand flow. Finally, these figures shows the evolution of sand dune field with and without turbulence. We can see from the third year of evolution that small-scale Barchan domes have been formed with turbulence, while there were only small sand mountains in the case of without turbulence. Until the fifth year, the small scale Barchan domes with uniform configuration were formed in the sand dune field without considering turbulence. This indicates that the turbulence promotes the formation and the development of sand dunes, and thus promotes the evolution of the dune field. The quantitative comparison indicates that the turbulence increases the average height and the moving velocity of sand dunes, and the results with the turbulence are closer to previous documented field observation, which is published in Nature. For the height of sand dunes, the relative error is 9.2% without turbulence, and it is 4.1% with turbulence. For the moving velocity of sand dunes, the relative error is 10.4% without turbulence, and it is 6.3% with turbulence. Therefore, turbulence promotes the formation and the development of a sand dune field. Taking turbulence into account makes the simulation more accurate and thus cannot be ignored. This is my answer to your question. Thank you very much.
Okay, wonderful.
Oh, very good, very good.
Yes,
I got it. Thank you, thank you.
Okay, let's move to the next question by Yanfei.
Okay,
yes.
Thank you. This is very inspiring and very motivational. You probably have discussed this, but somehow I think I missed it. So in the first part, you talk about this upscaling. Second part, talk about the downscaling. But it seems to me there's something missing. For example, in the second part, you measure the electrical field. You reconstruct using the inverse approach to find out the spatial charge density. But if you do this forward simulation, the upscaling simulation, how does the charge evolve? So you have those sand particles, let's say colliding, bombarding each other. How is that process generating the charge into different particles? And eventually, also in the beginning, you showed the lightning in the sandstorm. So then lightning from mathematics, it seems this is just some localization event. So are you able to reproduce that kind of localization or singularity after you have simulated the charge evolution? So things like that, I just want to see your opinion on that.
Your suggestion is very important. I agree what you mentioned for the electric fields to the charge to mass ratio. It is not really up down top to down simulation. So I just use the downscaling inversion. So we don't use the simulation. I think it is there's some the difference between the simulation and emerging problems solving. So
let me pose a much simpler question. Let's say you have a lot of sands, and they are just colliding each other randomly.
Yes.
How do you generate positively charged sand grain, negatively charged the sand grain? Why do you have that kind of charge generation?
Yeah. Actually, we have not discussed in the studies what you mentioned. The question you mentioned. In my opinion, we focus on the issue which has strong relationship with the application. So if the question is both, I mean there is some scientific issues also has the real problem in application, maybe my interesting or the interest of our group's research interesting may focus on the both. So what you said is really a scientific question, but I'm not sure. In the practice,
Thank you.
Okay, we get the next question by Yujie. Please.
Thank you, Prof. Thank you very much, Prof. Zheng, for giving us such nice talk. We really enjoyed your talk. It's very interesting. So I just, in your results, I just found some very interesting things to me. In your slides, you show the different sand dune pattern. Three different sand dune pattern. I saw it. Some patterns they have few dots. Some patterns they have lines. Some patterns they have the big lines like that. So I just wondering what kind of parameter, the key parameter, controlling these sand dune patterns.
Thanks for your questions. Yeah, it's very interesting. According to the experience of simulation, we found the one of parameters is the thickness of the deserts. I mean, if the thickness of desert is higher, the shape maybe become the linear one. As I mentioned, at the edge of the desert, the Barchan dunes are a little bit common to say, and also another factor is the prevailing directions for 1 year. Sometimes in some region, in 1 year, maybe there are one dominated direction of wind, and sometimes there are two prevailing direction of wind, and sometimes 4. So different number of directions may be also influence the shape of the dunes.
I see. Thank you.
That, okay, thanks.
Sorry, may I catch up another question?
Okay.
Yes.
So thank you very much. So it's very interesting. You said the thickness of the model desert could control the sand dune pattern in your simulation results. It is very interesting. So I just wondering, in your experiment, maybe it is easy to change the particle of the sand. So I'm just wondering, the particle size of the sand could affect your result or not? Thank you.
Yes, the particle size will make a significant result. Yeah, sometimes the particles size is maybe larger than 500 micrometers, and sometimes only 10 micrometers. So the result may be different, especially for the sand ripples. The scale for different size of particles, the ripple size are very different.
Thank you very much. Thank you.
Okay.
So Robin, do you still want to ask?
Oh yeah, I think Zhigang just helped me clean that. But yes, thank you, Yujie. So hi, Professor Zheng. This is Robin Bai. I work with Zhigang as a PhD student. I'm incoming assistant professor at Northeastern at Boston. So I have two questions. Maybe first ask a more technical one. So from what we learned in fluid mechanics, we know when we want to transfer this kind of experiment from larger scale to tabletop, this follows up previously Tang's and Jimmy's comments. So we have to take care of this Buckingham pi theorem, which basically is some dimensionless numbers like Reynolds number to make them match. Then in this system, I think obviously it's a very complex system. So then I want to take it back. My question is more like, if I think about earthquake, then I think I know both the satellite data, for example, NASA provides all this data from satellites on the Earth, and the tabletop experiments are useful in that case. But in the Sandstorm case, my question is, since you have this large scale data as you showed, and also I think possibly you could have the satellite data as well. Is that worthwhile doing tabletop experiments or not? Or in other words, what can this kind of small scale experiments in the tunnel, let's say a wind tunnel or even smaller, can give us in addition to all these existing data?
Okay, maybe I'm not sure whether I understand your question correctly, but I try to answer your question with my understanding. I think in the wind tunnel, also in the field, the experimental results with the observation measurement are a little bit different. In my opinion, in my experience, I did some observation in the field and find the very large scale structures, which is in streamwise length maybe more than 5 meters, but in the wind tunnel, the nano number is a little bit low, so maybe the length of a very large scale structures are much smaller than what observed in the field. Also, by the observation data, they cannot they can satellite data maybe cannot reveal the detail of the turbulence. I just use the very large scale structures as an example to show the difference between the satellite data and the environment, the the observation data in field and the experimental data in the wind tunnel. So far, we have not analyzed the satellite data now, but I just guess maybe there exists this difference among these data.
Okay. So can I ask a second question out of my curiosity? So
Short one, please.
Okay, so I've been a victim of this sandstorm for 22 years. I grew up in Xi'an, and then I was in Beijing for 4 years. So then I think my question was around 2008, if we remember, around Olympics, the weather and all of the things in Beijing was just fantastic when I first did my college undergrad there. But then it turned worse over years. I remember in my first 2 years in college, we didn't have sandstorm, but then it started to have again. So my question is, what affects these sandstorm other than your efforts, for example, putting those straws, but how about humidity and rain drop and maybe pollution? I'm just curious about these. Why do they start to have it again after 1 or 2 years? I don't think it's a long range efforts, right? It must be some short range change.
So this question is very interesting, and I'm not sure how to say the environmental changes about the sandstorm's influence, but what I can say is we say a lot of the bad influence of sandstorms, but sometimes they have a good aspect. Maybe for the in the ocean, the sand particles or dust moved by the sandstorms can give the fish in oceans a lot of food and make the fishes growth.
I think I can comment a little bit, Ruby. I think the sandstorms in Beijing is getting much better in recent years.
Yeah.
If we date it back to 2008, I think there must be some special measurement which was taken, and it's very hard to know, right? It's a one-time action to protect the environment to ensure the Olympic Games to be held successfully. So, but nowadays it's a normal time, and I couldn't remember there's any sandstorm for this year in particular, and it's getting better, believe me. Okay, I think I should move to the next the questionnaire because we have 3 more questions. Professor Brian Cox, do you have you still want to ask, please?
Hello, everyone.
Hello.
First of all, Professor Zheng, that was absolutely fascinating. Thank you very much for that talk. I know nothing about sandstorms. Now I know a very little amount about sandstorms. I have this intuitive idea of a sandstorm, that it's a critical event. You either don't have a sandstorm or you have a big sandstorm. So you go through some transition. So I'm curious, and I think it might actually follow up with Dr. Bai's question, in fact. Is it possible to list the factors that govern the critical condition? Wind speed, water content of the sand, ambient electric field before the particles get airborne? And would it be possible, do you think, for you in your simulations to compute critical values for any or all of those factors?
So your question is, or maybe your suggestion is very important. We really should evaluate which factor is sensitive or the importance for the sandstorms. And sometimes these factors are coupled each other. So the simulation may be very important because we can control these factors. But in the experiment, or especially in the observation in the field, it is uncontrolled, especially for some factors such as the wind speed or the heat transfer, or the combination of the many factors. So the simulation, especially in the respect of mechanics, the simulation is important. But now, maybe in the experience, some the factors, affection is obviously such as the vegetable coverage and humidity and the such as wind speed. These factors are very important. How about the other factors? Maybe we need to study it in detail. But according to my simulation, I cannot give the answer for your question. I just can give these opinions. I'm not sure it is answer your question.
Oh, yes, you did. Thank you. I think finding critical values is hard. But you have the possibility of doing them. So that's really
I will try. Yeah.
It's a very important question, but it's also very tough. All right. Let's move to the next question by Chong Wang, please.
Hi, Professor Zheng. Thank you for the inspiring talk and all the answers to the previous good questions. I'm curious for why this straw grid works so well in controlled sandstorm. Is it more like a turbulent flow over rough wall, or is it more like because the electrical charge get changed because of this straw grid? Do you have any insights for that?
Oh, maybe one of the important effect is make the wind speed reduced. So the sand particles is not easy to taking off.
Okay.
Is that right?
Okay. Yes, thank you.
All right, 10, please. 10.
Hi.
Yes, yes, please.
Hi, President. Thanks a lot for the nice talk. So it's amazing to see that your simulation can run a few years. So that's a very long time scale. And so I have a very general question. I know that now we are trying to avoid this sandstorm. But now if you understand the mechanism and the control, I was wondering, is it possible you can harness the sandstorm to achieve some function to make this a better thing for to get some like good outcome?
So the question, actually, I'm not clear what your question means.
So my thinking is that now if you can understand this sandstorm, it's possible you can use the sandstorm to generate some like a good impact. So some new function from this sandstorm.
I'm not sure. I just want to. I'm not sure if we have a good understanding for the sandstorm, whether we can make a good impact. But actually, one of the importance is we can supply some or maybe we can revise the boundary conditions or initial conditions for the models of sandstorm forecast. And I think this is the mechanics problem. And also for the sandstorm, there are a lot of scientists in different disciplines to solve or to reveal or to make a better understand for the sandstorm. What we have done is just in the respect of the mechanics. And I think what we can do now is supply the more accurate boundary conditions and the initial conditions to revise or enhance the accuracy of existing model of forecast about the sandstorm.
Okay.
Okay. Yeah.
All right. Let's move to the next questionnaire, like GPP. So can you introduce yourself and ask the question briefly?
Hello. Okay. Dear Professor Zheng, thanks for your interesting talk. I do some inverse problems on non-destructive testing method, so I'm very interested in the inversion work about the electrical structures of dust storm. We know that some AI methods, such as machine learning method, are more popular today. What do you think this popular method their advantage in solving the inverse problem? Thank you.
Okay, so actually, I asked my young colleagues, Dr. Zhang Huan. He is the author of the Nature Communication recently published to try how to use another method to solve the ill-posed equations in mathematics. And recently he got some new results, but actually it is not for the electric fields, but maybe Yujie can later, yes, Dr. Huan Tang gave his new result.
Yes. Huan, I already set you as the most distinguished guest. Huan, can you hear me? Oh yeah, I think I saw him on the playlist. Yeah, just describe briefly why the new computational method like artificial intelligence be applied to your question, the inverse problem. What? Hello? Can you hear us? Juan? Juan?
Hello, can you help me?
Yes, yes, we do. Okay.
Just to show your recent results about the artificial methods.
Yes. 张焕，他的问题就是新的，比方说人工智能的办法，是不是能够用到你的反问题的求解过程中？他想看看有没有可能性。
Many thanks, Professor Zheng, for giving me this chance to answer this question.
Yes.
In my opinion, machine learning can be used for the inversion of electrical structure of dust storms. We always focus on solving inverse problems using the classical methods such as takeoff or regularization. However, to my knowledge, machine learning has been widely used to solve PDE and inverse problems. In a certain sense, machine learning is better than the traditional method. Recently, I have read a paper about using neural network to solving inverse problems. I can introduce it briefly. Detailed information can be found in this paper.
I think that's good. Juan. I think that's good. It's a positive, and I think he got the message. Yes.
Yes.
Oh, thank you. Thank you very much. So let's give the last opportunity to Li Qin. All right, Li Qin, please.
Sorry. Yeah, thank you, Professor Wei and Zheng. So I just would like to address Dr. Bai's first question. Just now he asked about the the satellite, the INSA data usage in sand dune formation. Because I'm from a science field, so I know we use the INSA data quite widely in this field. So that the INSA satellite only flight about this place, the minimum is 6 days. So if you want to get the precise data, you need 12 days, the go and up. So that's the reason in the 12 days, you have to make sure there will be no any wind in this field. So if we use the INSA, the satellite, to monitor the sand dune formation is very difficult. I think the wind, frequency is quite small, maybe, right? So that's the reason I can imagine the limit usage of the satellite in this field. But I also wondering, if the earthquake occurred in this field, then with the sand dune together, that will be even big challenge for the INSA people. If they want to monitor the earthquake deformation with the sand dune together, then it will make the data really messy. Maybe cannot see the signal. That's my answer. Thank you.
Yes, yes, I agree what you said. Yes.
Okay, thank you for your comments. So I think for the time being, it's better way Professor Zheng has been with us, sharing your message, talking with us, answer questions for 2.5 hours exactly. So I think it's time to give her a break. I will give the final remarks to Professor So, Zhigang, do you want to make a final remark?
Oh, final okay. Perhaps a final question for Professor Zheng.
So many questions.
Yeah, oh, yeah, well, because you have been passionate, I know this for some time. You have been passionate to promote extreme mechanics in China. Yeah, partly, of course, it's what you do in research, but partly because your position, a very visible mechanician in China, try to influence researchers and funding agencies. So what do you see, so within the context of China, so what do you guys do if somebody like you, visible, doing research in the area, promote it? What can happen in China in extreme mechanics? So will government actually add funding to this? What is the practice just to learn about China?
Okay, so so actually I just inspired by you to promote the extreme mechanics. What I want to do is on the one hand is the many researchers in mechanics should combine the scientific questions research with the demands of the society's development. And on the other hand, I want, or maybe I hope, the Chinese government departments pay more attention to the mechanics, since mechanics has been play a very important role to push the society progresses. But actually, no matter the department, government departments, as the education department education, or the Department of Science and Technology, even including the NSFC, maybe, in my opinion, not pay enough attention to the mechanics. So, especially in China, the industry development should be development rapidly. So in that process, it is really the mechanics play a very important role. So that's why, inspired by the Zhigang, I just followed your ideas and hope to push the extreme mechanics to get the one for the researchers and another for the government, and hope the government to give more support the funding or some project to the mechanics research. That's all.
Oh, thank you. All right, Yujie, what do you say?
Okay, thanks to you all, and thanks to Professor Zheng. I think it's time to close the webinar. I would like to say last words. Best wishes to everybody. Stay safe and stay healthy. Okay, it will be nice to see you next week. for the webinar.
Okay.
Okay. Bye bye. Thank you.
Okay. Bye
Thank you
bye.
all.
Bye. Thank you all for your
Yeah.
attention and the suggestions and questions. Okay.
All right. Thanks. Yeah. Bye bye.